So we're going to finish off Chapter 9 today. We've already talked about how to search an array. You just start at the first element, you iterate through it, you check index 0, you check index 1, you check index 2, and when you finally have a match, you break out of the loop. And if you never find it, then it wasn't in the array to begin with. So now we're going to talk about selection sort. There are many different sorting algorithms with varying degrees of complexity and efficiency. We're going to cover a simple sorting algorithm. There are lots of simple sorting algorithms, and then there are some more complex ones. Some of them are kind of difficult to understand, actually. Those are the ones that are more efficient. But the simple ones typically, just start at the beginning and then they run through the end doing some kind of swapping. Those include the bubble sort and the selection sort. So what we're going to do is we're going to talk about it. What a selection sort does is it runs through the array, finding the lowest value, and then it makes that one the first by swapping them. So starting with 0, that's the lowest value, right? Well, not really. We compare these two. It's still the lowest. We compare these two. -3, that's our new lowest value. Is 20 less than -3? Is 2 less than -3? The answer is no. So those are the two that get swapped. Now that they've been swapped, -3 is in its correct place. So now we can just check these 4. We don't have to check all 5. So we're going to set our temporary lowest value equal to 10, and we're going to start comparing. Is 10 less than 5? In fact, it is. So 5 is our new lowest. Is 20 less than 5? No. So 5 is still our new lowest. Is 2 less than 5? Yeah, it sure is. So this is our lowest value now. And so we need to swap it into the second position. And we do the third, right? So this is our lowest value. We check 20 less than 5? No. 10 less than 5? No. So it doesn't even need any swapping. Starting here, this is our new lowest value. We check it to 10. Is 10 less than 20? In fact, it is. And now we've hit the end of the array. We've got to swap them. Then we're done. So we have an animation. Covers this idea. See if I can stretch this out a little bigger. Give ourselves a notepad. So if we start off at 0, because that's the first position in the array, the current lowest index is 0, right? Because we haven't found any lower values. And the current lowest value is equal to the position at 0, which is currently 64. Now we're going to play the video. Isn't that fun? You're watching a video of a video. So we go through. Our current lowest value is 64. We check it against 25. Aha! 25 is now our current lowest value. So at position 2, right, 0, 1, 2, we have a new current lowest index. And the value of that piece, okay, it went a little bit too fast. Firstly, at index value 1, that became the new lowest value because 25 was less than 64. Then it incremented I to 2, right? It checked again. Is 12 less than our new current lowest value? Indeed it is. So our current lowest index becomes 2. And we're going to keep searching, right? So our current lowest value is now equal to 12 because that's the one at position 2. Then it's going to go and check I is equal to 3. And is 22 less than 12? No, it's not. So we skip it. We don't update that or that. And then we're going to check 11, right? And so when I is equal to 4, we do one more check. Is 11 less than 12? It sure is. So that's index value 4 is the current lowest index, and the current lowest value is 11. And then we swap 64 with 11. So we swap position 0, our starting point, which was at 0. We swap those two. So we swap elements 0 and 4. Let's play a little bit more of the video. Now it's going to swap those two. All right. Now, our starting position is 1 because we know that this is the lowest value. We don't need to check them anymore. And so I is 1, right? The current lowest index is equal to I. The current lowest value is 25. And we're going to start the check again. As I increments, I becomes 2. Is 12 less than 25? It sure is. So our new current index, our new current lowest, is at position 2, and it's equal to that 12. And then I becomes 3, right, because we checked that one. Is 22 less than 12? Nah, it's not, so we don't update anything. And then we increment I to 4. Is 64 less than 12? No, it's not, so we don't increment anything. So the lowest position, the index of the lowest value is at 2. And our starting position, I don't know why I wrote 25 there. Our starting position is there, right, index 1. And so we swap values 1 and 2. That's what it's going to do again. Finds the lowest value, which was 12, and it swaps the position of that lowest value with the current one. Going to do it one more time. What's our current index that we're going to start checking? 0, 1, 2. We're going to start from 2. And so I set to our start. We check these two, right? So we're going to check position 3 against position 2. The current lowest value is at position 2. It's 25. We're going to compare it to 22, right? We're going to compare it to the item at index 3. It is, in fact, excuse me, that was the current lowest index, which was equal to 25. Dadgummit. Current lowest index is equal to our starting point, 25. We compare it to the next one, so I is equal to 3. We check, and in fact, 22 is less than the value position at that position, and so 22 becomes our lowest. Then we increment I, which position 4, our current lowest index, became updated with that one. Position 3, our current lowest value became updated with that, 22. And then once I is incremented, we compare 64 to 22. Is 64 lower? No. So our current lowest index is 3. Our starting point is 2, and they get swapped. We're going to watch that. So this is the selection stage, finding the index of the lowest value remaining in the array, and then we swap them. Then we increment our counter so that we're checking the next position. We're going to do the same thing. Find the index of the lowest value, and then we're going to swap them if need be. And now we're done. And here's some code for it. All right, if you feel like looking for that yourself, you can go up to selection sort. Search for selection sort geeks for geeks. All right. I'm not really sure that I'm going to require you to implement that. I bet the code for it's in the book anyways. If not, you could look at it right here and figure it out. So why would you want to bother to sort? Because searching a sorted array is much faster than searching an unsorted array. Like if we were back at our original data, like that, and we wanted to find the value 25, or the value 22. Let's say the value 22. Or even better, the value, 22. You'd have to start here. You'd have to, is that equal to our target value of 22? Nah. Okay, we increment to the next one. Is 25 equal to our target of 22? Nope. Is 12 equal to our current target of 22? Nope. Aha, we found it. So it took 4 searches. What if we were looking for one that wasn't even in here? What if we were looking for a 3? Is 64 3? Nope. Is 25 3? Nope. Is 12 3? Nope. Is 22 3? Nope. Is 11 3? We have to go through the entire list in order to determine that that value was not in the array, which is quite plausible. Okay, so if we go to the sorted version of the array, right, it's sorted now, and we're looking for 22. We can just stop as soon as we find it. pretty much the same as before, right? Check to see if it's equal to 22. No, it's not. 12. No, it's not. 22. No, it's not. Okay, great. We found it. We've been out of the loop. But the performance gain comes, one of the performance gains come when you're looking for a value that does not exist, right? Say we were looking for 13. Is 11 equal to 13? Nah. Is 12 equal to 13? Nah. Is 22 equal to 13? Nah. But we don't have to keep going. Why? Because if it wasn't before this 22, it can't be in any of these others because they're sorted, and we know no value past this point could possibly equal 13. So we can bail out. So in general, in order to determine if something is in the array, and if it's not, you have to search all the way to the end, unless it's sorted, in which case you can start at the beginning, go until you have verified that it's not in it, and once you find a number that's larger, you can bail out early. That's a significant performance gain. Another reason that it is far more efficient is you can do what's known as a binary search. The way a binary search is, imagine that somebody tells you to guess a number between 1 and 100. You guess 50. You take a spot in the middle. But our secret number, say, is 20. We're looking for 20, right? Here's our secret number. Our current guess is 50. Did we get it right? No, we didn't, right? So we were told, nope, that's too high. So we cut our guess in half, right? So we say, it's got to be lower than that. So we make a new guess, 25. Is 25 equal to our secret number? Nah. So the guy playing our game says, nope, smaller still. And so we cut that in half, right? Now it's got to be a value between 25 and 12, right? And we guess 12. Nope. Sorry, you guessed too low. It's higher. All right, well, it was higher, and it has to be between those two values. Well, why didn't I guess 19 or 18? Alrighty, is 18 equal to 22? Nope, sorry, dude, you're still too low. All right, but we know that it's between 18 and 25. And we keep chopping the list in half, right? So now it's somewhere between 25 and 18, which might be 22. I'm not doing the calculations precisely. But, you know, again, we got halfway between that one, and we just happened to get it right. So it took us, 5 guesses to find it. Whereas, if you were an idiot and told to guess a number between 1 and 100, and you didn't have the idea of searching in half, right? I'm going to guess 50. No, I'm going to guess 25. No. Okay, it's going to be halfway between those values. It might be 37. No. Okay, halfway between 25 and 37. You keep cutting it into smaller and smaller items, right? Significant performance gain. Because if you didn't have that idea and you just said 1, is that right? And they said no. So you said 2, no. 3, no. 4, no. It would take a maximum of 100 times, right? If the secret number was 100 and we started at 1 and just kept going up, we'd have to make 100 guesses to find it. On average, we'd have to make 50 guesses. If you're doing a binary search, doing this business where you start in the middle and you cut it in half and you cut it in half again and you cut it in half until you zero in on it, it takes at most 7 searches. That can be mathematically proven. No matter what the number is. Within 7 searches, if you execute this perfectly, which I may not have been doing, I was kind of close. But if you execute it perfectly to find a number between 1 and 100, it only takes a maximum of 7. And on average, it's less, like 4 or 5. Don't know the average. So that's a binary search. So-called binary because it cuts the list into 2 pieces. I wonder if I can find a video that shows that real fast. This one looks like a pretty good one. At least it's short. Now I'm just going to let them narrate it.
Now that we have some tools, we can dive into basic algorithms. Let's say you have an array sorted in numerical order, and you want to see if a number that you have exists in this array. If you start at the front and check every number in the array, the time could be big O of n if your number is really big. The same happens if you start at the other end You could have a really small number and it might end up taking linear time in worst case. However, we could do a cool trick here that takes advantage of the fact that you have a sorted array. Rather than starting at the end, let's say you started in the middle of the array. You could say, is my number bigger or smaller than the one in the middle? Since my number is bigger, I know that it'll have to be in the second half of the array. Now I don't even have to search the first half of the array. The best thing about this strategy is that you can make the same assumption again just on the second half of the array. Check the middle element and then move forward from there. My number is still bigger than the middle of this array, so now I only have to check the last element. And now we're at the end. We've checked 19 and 29, two numbers side by side, and we still don't see 25. Thus, we can conclude 25 does not exist in our array. Guess what?
So you saw what it was doing. We were looking for a 25, so we searched that position. Nope. So that cuts the array in half. We only have to worry about those parts. So we jump to the middle there. 25 there. Nope, still too small. So we cut the array in half again. Right now we only have one piece to check. If we were looking for a 29, great, that would be it. If we're looking for a 25, nope, not it. Okay, so we have determined it's not in the array. If we were doing what's known as a linear search, we start from the beginning and go to the end, we'd have to check all 7 values to rule it out, right? Or even if we were taking advantage of the fact that it was sorted, right? We'd have to go all the way to the very end. Is that 25? No. Is that 25? No. Right? We'd have to go down there. Now, if we were looking for a smaller number, we might get the performance gain, you know, of being able to bail out early. Say we were looking for 14, right? We're looking for 14. Nope, that's not it. Nope, that's not it. Nope, that's still smaller. Nope, that's still smaller, but we're still looking for 14. No, that one's too large, so we know that it's not anywhere past here. So binary search is by far the fastest sort algorithm you can get. That one might be worth coding. Let's go ahead and code that. Make a new project. I believe this is lecture K. Create your file in your favorite fashion. All right, let's make an array and then let's sort it. I'm going to make a very simple array. It'd be fun to fill it full of random numbers, right? Something like that. So an array of 20, whatever, doesn't really matter. And we can fill it with random numbers. So we need to create a random number generator. Here's a random number class that we can use. Unlike the math class, it's not all static members. Why? Because it has to maintain the state, some state information so that it knows how to generate the next random number. You may have heard the term pseudo-random. Pseudo-random just means that it's algorithmic. And it's really the only way of creating a random number with a computer, unless you know something that I don't. Like, you know, you can check the number of gamma rays that hit a cell or something like that. It generates some physical random number. Normally, the way a pseudo-random number works, don't bother typing this if you're typing along, right, is the first number is chosen algorithmically, or you can even select it, and then it figures out the next random number. Say our algorithm for random numbers is just we add 7 to it every single time, and then we modulus it by 4. That's probably a really stupid algorithm, but that's going to be our formula. Is x is equal to x plus 7 modulus 4. Well, unfortunately, you know, that has a higher precedence. So this is our dummy pseudo-random number generator. So we start up with 6, right? And so 6 is our first random number. Then we run it through our algorithm. 6 plus 7 is 13. Modulus 4 is 1. That's our new random number. All right, then we iterate it again. 1 plus 7 is 8. Modulus 4 is 0. Cool deal. See, we got these numbers. And if you didn't know the algorithm, you wouldn't be able to predict them. right? Okay, let's feed 0 into our algorithm. Get the next one. 0 plus 7 is 7, plus 4 is 11, and 11 modulus 4 is 3. So, so far we've generated these numbers, 6, 1, 0, 3. Nobody would be able to predict these if they didn't know the algorithm. Let's keep going until we get the sequence to start repeating, right? So 3 plus 7 is 10. Modulus 4 is 2. 2 plus 7 is 9. Modulus 4 is 1. 1 plus 7 is 8. Modulus 4 is 0, right? All of a sudden, we start repeating, right? And the sequence is going to be the same every time. And so that's the deal about pseudo-random numbers, is that if the starting point is the same, the sequence is going to be the same every single time. And so you have to worry about that in some languages like C and C++. You have to give it a starting seed that is determined in some fashion that's difficult to predict, like the number of seconds since midnight, something like that. In Java, we don't have to worry about it. The Java class goes ahead and picks a starting point for us. But it's algorithmically determined. And if you start it at the same point each time, you get the same sequence of numbers. Well, anyways, let's go and import our Java class. I put a package in here by mistake, didn't mean to. Anyway, so I'm going to add import at the very top, java.util.random. Why are you saying please wait? Pop up my random list. Hurry. Okay, fine. Anyways, there it is, java.util.random. We want to fill this thing with random data. So we're going to start a for loop and we're going to go from 0 up to, but not including the length of the array. So for int I equals 0, keep going up to, but not including the length of the array. So I is less than nums dot length semicolon. I plus plus, typical. And then nums is equal to, oh, we don't have our random number object yet. Let's make that. So random, R&D, doesn't matter the variable name, is equal to new random, parentheses and parentheses. This is the object upon which we're going to make calls. We're going to call instance method. So R&D dot next int. And we need to specify the boundary. Right? What is the boundary? Well, it starts at 0. And it'll go up to, but not including the upper boundary. Let me make sure that's the case. What if it could get all the way to the upper boundary? What do I mean by that? If I type in 10, is it going to be a random number between 0 and 9? Or is it going to be a random number between 0 and 10? And I have an error here. I better check the documentation on nextInt. So I highlight that. I click Show Java Doc. And for Pete's sake, doesn't work. Okay, fine. Random.nextInt Java. NextInt generates the next pseudo-random number. It should take an int as a boundary. Returns a pseudo-random number uniformly distributed between 0 inclusive and a specified value exclusive. Okay, so it is exclusive. Unlike Python, where if you say random number, 10, it'll go all the way up to 10. If you say random number 5, 20, the series of numbers that are possible between 5 and 20. In Java, it would, only go up to 19. Let's take a look. Why in the world is this not working? rnd.nextInt. I'm going to put my number back in there, and I'm going to go and click on the error and see what's possibly wrong, because I just read the document. Oh, and incompatible types cannot be converted to an int. Okay, I was an idiot. Nums is an array. We need to specify which element of the array it is. You probably had already spotted that, right? So num subscript is 0, subscript 1, subscript 2. And there we go, right? That's our random number. It's our random number array. Start from the beginning, go to the end, filling it with random numbers between 0 and 9. And let's print out our array, see what it looks like. System.out.println, parentheses. And let's just print it the really easiest way. Arrays dot, is it array dot Are you really going to do that to me? Nums dot toString. Okay, sorry, got how to do it. Nums dot toString. That'll sort it. Excuse me, it won't sort it, but it'll print it. Let's make sure that's the case. Let's print it. Yeah, there's a little warning over here. And it failed. All right, what was our error? Class interface or enum expected. My brain is on a glitch. Why did that not work? That's supposed to be array dot toString or arrays dot, there we go, arrays dot toString, and we pass in the array that we're trying to print, right? Nums. Yay. Oh, what's wrong? I just never included the array class. Right. So I can run up here and add the import for it. Oh, look at that. We're even getting a package here. Everything's going wrong. We'll fix that. So what's wrong with his add an import for java.util.arrays? If I come up here and just change this to java.util.star, we'll be good to go. And what's this one? Class interface or enum expected. Wasn't that just working earlier? It should not be this difficult. All right, I'm an idiot. The package statement has to come first. I should have just let netbeans add the import. You probably knew that. I hate package statements. Messes me up all the time. So what I'm going to do is I'm going to click on the package, remove it completely. That's going to generate an error because it's no longer in the correct directory. A couple ways you can fix it. The easiest way is just click on the error and say move class to correct folder. So it takes it out of the subdirectory, it takes it out of the package directory. All right, now I don't have to worry about the position, of our imports compared to the position of the package. All right, I apologize for that fumbling. Let's go. Hammer and broom. Green arrow. And we have a pseudo random series of numbers, right? If we ran it again, the numbers should be different. What if we set the seed? The seed is the starting value of it. So R&D dot set seed. I'm going to just set the seed to 0. Seed's the starting value, right? And so that gets fed into the algorithm. So now it's going to generate the same series of numbers each time. Right, 0, 8, 9, 7. Let's prove it. Run it again. 0, 8, 9, 7. Right. So if you need the same data every single time, set the seed. The same series of so-called random numbers, right? You're writing some test sequence, some test code, but you really want to feed it the same series of numbers each time. Set the seed. But if you like for the numbers to be, more random, like you're writing, some kind of game that involves rolling dice, it'd be a real drag if the dice were always generated in the same order. Then you wouldn't call set seed. I don't mind leaving that in there. I also don't mind commenting it out. I'll add a comment here. Use set seed to specify the starting point for the pseudo-random algorithm. If you do, it will generate the same sequence of numbers every time. Alrighty, we have an array. Let's write some code that will search the array. Let's go and make it a method. Since we're in a static context, it needs to be a static method. So public static int search array. And it's an array of ints, so we need to pass that in. Just going to call that AR. And our target. So we need to set our found at equal to -1 because we haven't found it yet. And then we're going to make an array that searches from the beginning to the end. Just another for int or int I is equal to 0, I is less than the length of the array, so ar.length, comma, or semicolon, I plus plus. All right, let's see if we found it. AR if parentheses our target equals that current position, if target equals AR subscript I, and we found it. Found underscore at equals I. We could even break from the loop at that point. We're going to add a break. This is just for efficiency so that we don't keep searching it. Like if it's at the second number found, we don't want to keep going, to all the rest of the 20,000 values. So break out of our loop. This is the end of the for loop. This is the end of the search array method. And by the time we get after the for loop, we've searched the entire array and we return the index of where it was found. And if it wasn't found at all, then that still equals -1. Okay. So let's search. Let's search for a specific value. Why don't we look for the value 7? So int found underscore index. We could even call it found at, right? Just tell us if we found it or not. Found at is equal to search underscore array. We need to pass in the name of the array, which is nums, and we've got to pass in the value that we're looking for. 7 is our target. If search array returned a -1, it meant it didn't find it. So what's our code for this? Our comment, search the specified array for the specified target, return the index of the element that matches, or -1 if not found. It'd be really nice if you documented your methods to describe what they do. So down here, found at is equal to search array, and if it's equal to -1, we didn't find it. If found underscore at equals -1, system.out.println. I should have stored that in a variable so I can print it out right. I'm just going to say target not found for 7 not found. I can't help it, I want to make it correct. So int target equals 7 and then pass that in as an argument, right? So then I can say, did we find the target? No. Target plus quote space not found. End quote, end parentheses, semicolon. Else we did find it, right? System.out.println parentheses quote, or no quotes yet. Target plus quote space found at index space end quote plus found underscore at. And that's our code. Let's add a comment down here at the bottom that this is the end of main and this is the end of our client class. Just keep track of things. Let's run it. It did find a 7 somewhere, index 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, seems to be working. Let's keep going. Eventually, we should be able to find it. Generate a series that does not have a 7. Who knows how many times. But in fact, it found it at position 1. That's correct, 0, 1. I'm just going to keep clicking the run button until aha, there it was, and I skipped past it. Ran too many times. All right, 7 not found. So it did work. It did work successfully. If that data was sorted, it'd be a lot cooler. There may be an arrays.sort method that would do it for us. In fact, I know there is. Arrays.sort, and you pass in the array. And then let's print it out again. System.out.println, parentheses, arrays.toString, lowercase t, capital S, parentheses, nums, our nums array, close parentheses, semicolon. All right, at this point, our data should be sorted. In fact, it is. That means that we can take advantage of the fact that we can do a binary search on it. I'm not going to write the binary search because they give us one. You know, I could assign you something, you know, to write a binary search, but I don't want you to have to memorize that algorithm. If you go on to get a 4-year computer science degree, you certainly will write a whole bunch of sort algorithms, including that one. So let's find it. Let's find the position. Found_at equals arrays dot binary search parentheses nums, and we're going to search for our target. Then we can print out that it was found again and not, right? So let's make absolutely sure we know what binary search does. If it returns a -1, it's going to at the least return a value less than 0. Some search algorithms return an index which was the last position it found before it ruled it out. Right, if we were looking for a 12 and it never found it, then by the time it kept cutting it in half, you know, it might have determined that it didn't exist at position 8. And so that's useful information. So it would return a -8 to indicate that, well, the closest one in there was at position 8. So it just returns a negative version of it. So if parentheses found_at is less than 0, means we didn't find it. Show the Java doc on it. Oh, you arrays.binary search Java. Returns the index of the specified key if found within the specified range. The return value will be greater than or equal to 0 only if the key is found. Now, it's not talking about that business of returning a negative index, and I really think that it does that. So let me find the official documentation on Oracle. Returns the index of the search key if it is found, otherwise it returns negative insertion point, which is the point of where the key would have been if it was in the array. The last value checked, the last position checked before it decided it couldn't find it, which is useful information. Like if you need to go and find the nearest version, you need to know where to insert something into the array. If you find some, you know, code that's capable of inserting into the middle of an array. Is there an arrays.insert method to make that easy? Usually you can't insert into an array because it's a fixed link. Sorry, there's some noise out there. Arrays.insert. No, all right. How do you insert? You create a new array that's one longer in length. You copy all the elements necessary. Then you put the new element in the right position, and you copy all the other elements. Okay, so if found_at is less than 0, means we didn't find it. I'm going to cheat, copy these. So if found_at less than 0, then print out not found with selection sort, else found with selection sort. And our search array method, we should make a comment in the documentation to the effect that it's a linear search. So I'm going to scroll back up here. Search the specified array for the specified target with a linear search. Linear just means starting at the beginning and going to the end. All right, so if it found it with the linear search, it should be able to find it with the selection sorted up as well. And in contrast, if it doesn't find it. Okay, we would increase the likelihood of it not finding it if the range of numbers was larger, right? If the range of numbers was between 1 and 20 rather than 1 and 10, then fewer 7s are going to be generated. We're not going to see that number quite as often, so we should get the not found message more often. So I just generated a random numbers with larger range, right? Now they're going, from 1 to 19, 0 to 19. I don't see any zeros, but they're there. 7 found with selection sort at index 9. 7 found at index 1, right? So it found it at the very beginning, right there. And when it was sorted, it was, there. I'm going to keep running it until it says not found. And true enough, right? But the performance improvement was at a linear search. Our search had to go to the very end. So it had to search all 20 elements before it could rule out that if there was a 7 in there. For the binary sort, it starts in the middle. Excuse me, a binary search. All right, 7, nope, that's too high. Come to the middle here. 8, nope, that's still too high. 5, nope, that's too low. 6, nope, that's too low, right? And then that one, nope, that's too high. So it ruled out. And so, the position where it should have been, 0, 1, 2, 3, 4, 5. So it's going to return a -5. Or maybe a -6. I don't remember, about the exact return value. Let's find out. Let's just print the return value. System.out.println, parentheses, quote, binary underscore search, return, space, end quote, plus, and I'm going to wind up commenting this out because it's confusing information. We don't really need to know where it would have been in this particular case. But I want to see that. All right, 7 was found, 7 was found, 7 was found, 7 was not found with selection sort, and so it returned the -1. I don't think it's doing a binary search. I think I'd call it a search method. But at a binary, no, it should have been. Okay. Forget that business about the negative value. It's not working. You could research it a little bit more if you want to get it to work. Forget it. Not getting it right. All right, I think we're pretty much done with the chapter. Let's go look. Any other topics? Sorting the array, selection sort, two-dimensional arrays. Oh, I thought we were done, and we're not. Can I talk about two-dimensional arrays in 10 minutes? I believe I can. What is a two-dimensional array? It's just a grid. You are real familiar with two-dimensional arrays if you use spreadsheets, right? So if I launch Excel, it's just a grid. You play Battleship as a kid. You sunk my battleship, right? Okay, what's the position? I'm gonna guess that it's position A3. Nope, it's not at A3. Okay, then is it at D5? Nope, it's not at D5. All right, Excel sure is taking a long time to launch. Anyways, so we have a two-dimensional array. We've got columns and we've got rows, right? So it's not A3 and D5 because everything is referenced by a number, of course. So you just imagine a two-dimensional array as a grid like that, commonly called a matrix, except both the row number and the column number are specified by digits, no letters involved, and it starts at index 0. So this would be 0, 0, right? Because it's in row 0 and column 0. This would be in row 0, column 1. This would be row 0, column 2. This would be at 1, row 1, column position 0. This would be row 2, row 1, column 1. And this would be row 1, column 2. 2, 0, row 2, column 2, row 2. Wait, I skipped 1, right? Column 0, column 1, column 2. All right, so we have 9 positions. This is a 3 by 3 array, accessed by row and column. You allocate a two-dimensional array with a pair of braces. They're showing that you can initialize a two-dimensional array the same way that you can initialize a one-dimensional with an initializer. Why not? Let's do that. You go close the door. All right. So I'm just going to call it grid. It's a two-dimensional array, so we need 2 sets of square braces. Int square square grid equals, and we're going to use an initializer list. Now I'm going to make this a fairly long initializer list. All right, so the first row of our grid is going to have these numbers: 8, 6, 7, 5. That's the top row. End curly brace, comma. Now let's add a second row. 3, 0, 9, 0. End curly brace. Now let's add a third row. 3, 1, 4, 1. Let's add a fourth row. 3.1415, 9, 0, 0. Whatever. The numbers don't matter, right? And then a closed curly brace, and we are done. So we have declared a two-dimensional array consisting of 4 rows. Each row consists of 4 items. Now, usually you don't know your data in advance. So if you're going to allocate it, it'd look like this. Int grid 4 by 4 equals new int 4, 4, right? Or what if I was going to make it, different size, like 5 by 5, 5 by 2, 5 by 3, whatever. I'm going to make it a 3 by 5 array, 3 rows with 5 elements each. So my name is now wrong, right? I'm just going to call it grid 2. Alrighty, to access the elements in a two-dimensional array, you use a nested loop. Say we wanted to print it out. Why a nested loop? The outer loop is going to step through row by row. The inner loop is going to step through every column in that row. And there are some slightly different ways of doing this. I'm going to do the way that makes most sense to me. For int row equals 0, row is less than grid dot length. Now grid dot length returns the number of rows in it. So if we call it grid dot length here, it's going to return 4 because it's 4 rows. If we call grid 2 dot length, it's going to return 3. That's important to remember because dot length does not have anything to do with the number of columns when this is a two-dimensional array. All right, and then lastly, we need to increment our row counter there. Our inner loop, which steps through the column of that row. Ooh, why are you giving me in there? Oh, because I put a comma there, like an idiot. There we go, semicolon there. For int column equals 0, column is less than the length of the current row. The current row is grid subscript row dot length, right? So what is the length of this row? Well, it's 4. What is the length of any row in this array? 5. So the outer loop is going to count from rows 1, 2, and 3, or more specifically 0, 1, and 2. The inner loop is going to count, 1 to 5, or specifically elements 0 through 4. Right? Notice semicolon, call plus plus. Let's just print it out. System.out.printf, parentheses quote, %. These are all ints, so I'm just going to use D, but I want each one to occupy the same space. So I'm going to do %4D, comma, grid subscript row in subscript call in subscript in parentheses semicolon. Now when I'm done printing out that row, I need to print a character term. So I didn't add the \n right there. Instead, I'm just going to do a system.out.println right here. Right, because once you get to the end of the row, you're done. All right, so this will print out every element in our grid, in our two-dimensional array. And in fact, it did. What if you wanted to calculate the total? We can do the same thing. Let's calculate the total for grid 2. Int total or double total, if you're going to be calculating averages, double total equals 0. For parentheses int row equals 0, semicolon, a row is less than grid 2 dot length, semicolon, row plus plus in parentheses. For parentheses int call equals 0, semicolon, call is less than grid 2 subscript row dot length in subscript dot length, the length of that specific row, semicolon, call plus plus, close parentheses, and then total plus equals that specific element, grid 2 subscript row in subscript call in subscript. And remove that close parentheses, which was unnecessary. Now I didn't even print out grid 2. Right, I just printed out the grid here. But whatever. We now have the total of grid 2. We can calculate the average. What's the average? Well, how many elements are in a two-dimensional array? Two-dimensional array has, well, this one has 16 elements. How to get that? 4 rows times 4 columns. This one's got 15 elements, 3 rows, each one's got 5. So int num underscore elements is equal to grid 2 dot length multiplied by grid 2 subscript, it doesn't matter which row we pick. How about the first row? Dot length. Or we could just keep a counter of how many elements we found. So I'm going to come up here and say int count equals 0. And every time we add 1 to the total, we're going to add 1 to the counter. But we could have calculated it the other way as well. Then we could calculate the average. Double average equals to the total divided by the count. And since I made total a double, then we're safe, right? It's not going to do any integer, division and rounding down. We get a value with the decimal place. System.out.println parentheses quote average of grid 2 equals space end quote plus average in parentheses semicolon. Make sure we don't have any syntax errors. All right, the average of grid 2 is 0. Well, how about that? I wonder what I did wrong. Well, that's disappointing, especially since I really only have 2 minutes left to finish the lecture unless I Pause it and come back. Why don't we print the values out as we add them? Debug time. You don't have to do this until I find the fix for it. Grid 2, subscript row in subscript, subscript call in subscript. Oh, well, of course all the elements are 0. We never added any data, right? I just allocated it. So that is actually a correct answer. All right, so what's our homework going to be on this? Let's take that print statement out. Homework. Write code that will fill, that will prompt the user for a length of a one-dimensional array. The normal kind of array. The array that we've been talking about for a couple lectures. Allocate an array of that length. Fill that array with random numbers between 0 and 1,000. Well, so you're going to use randint 1,000 in order to get that right. Print the array, whatever means you want. Arrays.toStrings a totally cool way. All right, then. Copy that array into a new array. So we're going to allocate an array of that length called nums1. That's the name of the original array. We're going to copy that array into a new array called nums2. Sort nums2. You can just call, arrays.sort. Print nums2. And then search nums2 for the value 50, for the target value of 50. And print its index, or print target not found. That's part 1. I don't care how you search it. You could use a linear search, or you could use the search method, right? You could use binary search since it's sorted. Or if you feel like doing the linear search, either way is cool. I don't care. All right, that's part 1. Part 2. Modify our code from the lecture to fill grid 2 with random numbers between 0 and 9999. Print the array out as a grid with a nested for loop. That's enough, right? Just fill it with random data and print it out. All right, hope that makes sense. I'll post a video, upload this, and you can get to work on it.